Okay, so how do you set up microwave? It is important to have your bow to the positive x because we need to come to the forward speed. So waves coming from the x direction, then your bow needs towards that. If you have a bow the other side, when you have a forward speed, so that's really the following scene. First things you want to make sure when you set up a microwave, the frequency domain it says when you define the speed and the heading, you need to make sure your positive x towards the bow. Sometimes when you happen to have another model import from ANSYS or you build the model in a different direction, so you go to Maestro module. Actually, in this case, the model was developed, the x direction is towards the stern. Let's see here. We have to rotate that. In the beginning, the original model was like this. The way to rotate it back is first you have to create a substructure. For example, if you build your model, we can drag this to here. So we did that. Okay, so let's say you have a model like this, and you have 4 substructures. The full model is towards the axis towards the stern, and you need to rotate that. If you want to run the general FEA, you don't need to rotate anything. You have loads, you just run it. Since you want to run microwave, the first things you want to make sure you rotate that. You cannot just rotate one module, because you rotate one substructure. For example, if we want to go to here, it's the current. And if we want to say we want to rotate the sky, when you view it's all messed up. Of course, you can rotate one at a time. The orange location, you can fix that, but that's a lot of work. So usually what we do here, first you create a new substructure. Create a new substructure is called subs, or anything you want. You create that. Then you just drag the other substructure or module into here. Now you just rotate this substructure. So we go to here. This is the current. So you see a hand there, which means you can modify that. Now you say, okay, I want to rotate that guy. Modify. So the whole model rotate that. So the key is you need to make a substructure and drag and drop everything here to make that X towards the positive direction. And then you need to balance the model, right? We needed the mean surface line to run the hydrodynamics. You probably after your rotation, you do the rebalance for the inertial base. So the first load case, we call this the hydrodynamic load case 1. If you want to relate to the SMM file, that's your inertial base code. In this case, it's just there's a mass, scaled mass, module scaled mass, everything takes the same mass, and there's a floating hydrostatic buoyancy. So you want to make sure it's balanced. Okay. You usually check what's the bending moment. It's in equilibrium, right? Bending moment start at 0, end with 0. So now you say, okay, I can run the hydrodynamic. Okay, go to the view, get back. So to set up the hydrodynamic rounds, you go to the microwave. This is the frequency domain round. We want the motion and panel pressures. This is the loads. We want mapping the panel pressure to the FEA later on around the motion analysis. You can use in binary or you can use in text, the SML file. Those are a couple of choice for the tank loads. Usually we're using smear tank mass, the tank schemes. That's a certain case for frozen and sloshing, but in general, you just keep the default. We can talk about sloshing later. Mathematical equations are different. You set up this, say you want to create, modify, and the next tab, so I want to run water speed. You can enter here 0 to 5, dot, 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 3 dots, comma, 20. Okay, when you do that, when you place your cursor to a different field, it's going to generate every 5 dots. Headings, you enter same thing, okay, 0, 45, dot, 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 comma, 180. So that's every 45 degrees we run that. Well, I already have the same thing. So if I change that 0, 30, 180. So it's going to populate the headings. Now wave frequency, you can do like from 3 seconds to 30 seconds. That's the default. You can do the wave frequencies. That's the radius 0.01, 0.05, the same. Sometimes you say, I want to do the wavelength, the ratio to the LOA. These two are most widely used. People using just simple, hey, I want to use just the wave period, or using the wave frequencies. Wave frequencies last. It's pretty good. You'll figure it out later on when you practice a little. So let's do a little exercise here. We'll say 10 knots. We run 0, 45, 180. And we're using wave frequencies because it's less. From 3 to 30, that's 37 wave frequencies. It's a lot more rounds. Create a modifier. So generally, you say this is frequency domain rounds. You want to define the speed, the headings, and frequencies, and what kind of mesh you're using. We're using the original finite element panels because this is a really small model. We can do that. When you have a large model, we're going to talk about it later. You're probably using the patch elements, or you can use strip series. So those are faster. Well, usually for the panel code, we want to remove irregular frequencies. When you change that, you click create a modify. There's a damping approach. There's a number of methods. It's all documented in the literatures. Default is this B44, critical damping ratio K is 0.05, and you can change it. And you can use in other equations, bar method, Jones method, Ikita's method. So if you are expert on the motion, you can play with that. For the structure people, we probably just take this default. Wind flow, that's for the mooring part, and wind turbine issues, so you don't need to worry about that for now. And after you set up everything, you click compute. It's going to ask if you already have data. You say, do you want to override it? Say yes. So now it's running. You can hear from the output panel, it's saying, okay, we're running 0 speed, 0.5 knots, just keep running that. And here you can go to see the process. We want to have the name. So, oh, it's finished. Automatic finish is killed. I don't know if you got a chance to see that. There was process running there. After finish, it automatically asks whether you want to load the database. You say, yes, I want to load the database. So here it says finished loading. And then you can go to the wave. You want to see the regular database. We have one speech, different headings. Each heading, you have the wave frequencies. So you click on any one of that. Let's say 8 seconds. So this shows you the dynamic pressure of 0 speed. All the panels is the pressure as a point force, longitudinal bending moment, transverse bending moment. So if you have a catamaran, that becomes important. So all this data is for the union wave loads. If you right mouse click, it's going to give you some information. You want to list the bending moment for each sections, the IO give you that. At the pressure level, if you right mouse click, it's going to, do you want to see the pressure? So you can see the pressure of this round. So you can see it's negative. This is sinusoidal wave. And the different speed headings, you can see was the phase angle 0, phase angle 90, or any phase angle you want to see. Okay, you want to see 6 degrees, what's the pressure look like? So you can enter those. You generate a database, you can review that. You can also review in the curve, like motion. I want to see the head see what is motion IO. This is the wave view IO statistic time series. Let's, for example, we want to see the heave. You can pick any point to get the heave motion of that point for this speed is heading. If you don't select anything, that's going to plot the CG. Button you click plot CG. Okay, CG always plot at the x equals 0. We give you the output here. What station? The CG, wave frequency, motion IOs. Okay, motion IO, load, that's a lot of stuff. You can play with that. Sometimes you say, I want to see that in Excel. You select Excel. So when you click plot, it's going to generate Excel for you. That's the Excel. We dump the same data to Excel, and you can see the heave motion from the time or the wave frequency, omega. Motion person, you probably need this a lot. When you have a load database, you can clear this because the wave clear plots. For the structure people, once you finish load database, you usually want to say, I want to generate. Before doing that, in a irregular wave, we want to define what's the wave scatter diagram. In Maestro database, you can import a wave scatter diagram, go to the import, wave, C drive, Maestro data, hydrodynamics. So there's some default C scatter diagram. That's IX. You just click that, import it. Your wave scatter diagram. Now you have two of them. One is the original one, and you can use the new one. That's the data. We'll talk about how you enter that in a different class. You have this, and you need to define your operating profile. You don't have operating profile. There's a library. For example, for a combatant, saying for 5 knots, head C, what's the probability? You can make it up. You can define that. But if you don't want to define anything, that's a nominal operating profile. So you can use that. So when you have speed and the heading operating profile, you can generate your design waves. Go to wave, compute design waves. This tree dialog shows you the database you just run will have one speed, 5 headings. You can have multiple speed, multiple headings, different headings. This is a long crest wave. You can change the short crest as well. Long crest wave, if you define, you will need at least one C-scatter diagram. And you can pick one, any one of you want to pick. And here is going to show you what's the C-scatter diagram. And operating profile, if you don't have anything, it's say every speed and the heading is equal probability. But if you have one, you can say, I want to use in this one. There's a couple of wave spectrum you can choose. Brad Schneider, that's blue water, deep sea. Usually that's what people use. You can use other wave spectrum like Youngswap and Poisson Moswick and so on. Okay, that's a couple of C-scatter diagrams available in the literatures. You can add your own C-scatter diagram. Okay, pick that. You can say that's the probability level, how many waves you're going to see in your lifetime. 1 to the minus 8, I think that's 100 million. For 100 million waves, what's the maximum bending moment you will see? Or you can say, well, okay, this is 30 years design. You know, ABS equivalence, so 100 million waves and 30 years is pretty close. And you also can define what is the short-term minimum, which means if you run into C-state 8, what's your requirement? They say, at least I need half an hour. If you don't, it's just calculate the exposure time based on speed and heading and C-scatter diagram to calculate how much time is exposed in each cell. In C-state 8, for that wave period, that's how much time. It's just pure mathematics. But if you define at least half an hour or 10 minutes for any C-state, we're going to use in that as well. But usually you don't, you just take a default there. So here, this is default because that's how we finish microwave runs. We import it. If you have a different database, you import it and you don't have a balance load, you may want to recompute that. But for now, it just stay with the import. So there's a couple of design load parameters. This is called the design waves. Okay, we want to pick up the maximum vertical bending moment. You say VERT, BM. And vertical bending moment, you can specify a given station, right? We have 20 station cards. You can specify, so station 10, I want to check the maximum bending moment in station 10 of the lifetime. You can pick up a station, or you say, okay, just find the station for me. Check every station. Station 9 is largest, take that one. Station 11 is largest, take that one. So right now, I already have 3 load cases. The other 2 is design waves. So I want to go to more. I want to delete those. Let's go to wave, computer design wave. I want the combatant, 30 years of design life, maximum bending moment. Here it says how many design waves you want. We'll do the largest wave bending moment. If you say, give me the largest 10, okay? And so when you say add, we'll give you largest 10 wave. So this gives you the speed, the heading, wave frequencies, and wavelengths, and so on. So wavelengths, that's usually pretty close to your ship length. This is for the inch unit. And all this statistic calculation, what's the amplitude for your design wave, what's the phase angle, what C state is that. So that's 8.127. You can check that. So that's 1772, 8.6. So this guy is the worst maximum bending moment. First of all, probability is very high. This was also pretty high, but IO shows this is worse than that. So in this C state, you are running to extreme likely you have the largest bending moment in this C state. So this gives you all this information and how many wave cycles you are running to that. We give it the 10 largest. The reason for that is we don't need all this because they have the same headings. If the design satisfies the first one, it's likely satisfy the others. Load case number 8, it's a little different than load case number 1. Well, even though we don't have the largest bending moment, it's oblique C, 135 headings. Bending moment may be not large, but this one has torsion. So the combined loads, it is possible that could be a worse scenario than your head sees. So you probably say, oh, I don't really need those. I delete those and I just pick this. So likely these two load cases probably are concerned for the design. So now we have these two load cases. We say, okay. And now you see in the static analysis, we automatically add 4 load cases. This is a sagging hogging because it's a linear case. And this is another phase angle change from 0 plus 180. The design wave, as another thing I forgot to mention that you can do none, which means that's all dynamic. Or you can do the still water. The still water superposition, you are dynamic. That's the default. We're going to talk about this later. The ABS, when you're in a wave, is a nonlinear. You should impose a sinusoidal wave. From the linear theory, when you impose a sinusoidal wave, you violate the equilibrium. Then you have to do some adjustments. We'll talk about that later. So the ABS has an approach, but if you go to other class society guideline, they don't really recommend that. The math just didn't add up. Using the linear theory to calculate the hydrodynamics, then you put a sinusoidal wave, the nonlinear wave, you don't really have an equilibrium anymore. So that's how you generate a design wave. In Maestro, once you have that, you can just run it. So you just run the analysis, automatic restraint. So you finish the full extreme load case. So that's still water, hogging, second. Oh, I didn't have an equilibrium. I didn't run the initial relief. So all you can do the regular constraints. To recap that design wave, you can do the extreme bending moment. You add just one, or the extreme shear. You just keep doing that. Usually there's a couple of cases. ABS for the monohull probably need 5 of this. The first 5, VBM, horizontal bending, longitudinal torsion. Sometimes if you have an interest for specific accelerations, you can pick at that point. We'll cover that later. You enter that, you add, you have your loads, then you can just run it. To check equilibrium, we didn't do any initial relief or anything. We have a design dynamic load. You can view that. Go to the hull. I want to check the bending moment. So you can see it's closed. It's an equilibrium. Okay. And you can view the dynamic pressure. Go to the view pressure. That's this bending moment worst. It's a little oblique C. One side has more pressure, the other side is less. Bending moment is not the largest, but there's a little torsion. Could be another worst case. But maybe when you do the design wave, when you do the longitudinal torsion, it's possible to cover that case. After a while, you probably just need one. When you have too many load cases, a lot of cases to analyze. Even you do the first 5, you have 10 load cases. If you keep adding different DLP, then you have more load cases to run. Okay, that is the ELA. A quick review how you run ELA. You can see the slides I sent that to you. Speed heading, what do you set up? You're using the original mesh. Usually you want to keep that like 5,000 panels, even 10,000 today's computer is okay. It will take some time. But if you have like 20,000 elements, you want to use a different approach because otherwise it's going to take very long to run. If you have 100,000 elements, you're out of memory. So you can't really do the 100,000 elements, not in Maestro, not in any code. If you check the DMV code, they recommend like 2,000 elements. Above that, they say, okay, you got to do something. When I say 2,000, that's probably 10 years ago. Even 10 years ago, Maestro, you can run 5,000, no problem. That's that. damping. You can see that you have the result file,